We're like, okay, good morning. First Sunday of the month, 11 o'clock, which means it's time for Chai and Why. Welcome to all of you who've come here. Welcome to those who are watching this online. Today is a very special Chai and Why. And I'd like to thank all of you, the audience, for being with us for the last 16 years. And somehow we sort of, didn't really keep count. But we find that we've done many sessions. And just to say that Chai and Why is an outreach offering from TIFR, the Tata Institute of Fundamental Research. The first Sunday of the month, we are here at Prithvi Theatre at 11 o'clock. The third Sunday of the month, we are at Ruparel College. And if a month has a fifth Sunday, we are live online from a lab somewhere in the TIFR system. That's how it is right now. And we started in 2009. We've been going on without a break since then. So Chai and Why actually predates Chai Pe Charcha. I don't know who got that thing from where. And, I keep hearing that there are these things coming that ugly bar 400 par. Well, Chai and Why is always a bit ahead of it. So we are actually celebrating crossing 400. So this is the 400th session. Except that after all this fanfare and announcing the 400th session, Ullas, who sort of does the back end, everything for this, counted very carefully and found that we had one special session, which was at an intermediate venue. So it's actually 401, but theek hai 400 par. Okay. So it's not ugly bar 400 par, it is right now 400 par. So on that note, thanks a lot. Welcome. Please follow us. And the good thing during the pandemic, what we learned was it's very easy to be online. So those of you who are watching online, you will be able to get the main session here. Of course, you will not be able to get the chai and the discussions over chai. So that's the part you missed. You'll have to make your own chai. But still, I hope you enjoy it. You can, if you're online, please put your questions in the chat box. I will monitor the live stream and I will ask the speaker the questions appropriately or at the end of the talk. All of you here, you can, of course, raise your hand and ask a question if it's important during the talk itself. Or we will have the online audience does not get the chai and the question answer session after the chai. So the second half of the program is especially for all of you who come here in person. And you can also save your questions for then. That's absolutely fine. So on that note, it's a pleasure to introduce Professor Jayaram Chengalur, who is a radio astronomer and will be speaking on radio astronomy today. He is also the director of TIFR, and I am not going to bother introducing him. I'll let him do it, talk about his journey in science and in astronomy. And over to you, Jayaram.
Yeah.
And
so now you can trust him. Yeah, thank you so much, Arnab. So I've been hearing, of course, about Chai and Why for a long time. I've been in the TIFR system for more than 25 years now, although I've been in Colaba for much shorter than that. So I've been hearing about Chai and Why for a long time, and it's really a great pleasure to be here today and actually participating in this program that I've heard so much about. And, and really, congratulations to Arnab and his team for having kept everything going continuously, through the last 16 years. And I think even particularly during the pandemic, just making sure that this program keeps going. So just give me a moment. I'll just connect and start my talk. Yeah, so Arnab had asked me to introduce myself, but I think he's already said everything that's relevant. I've trained as a radio astronomer, and I work at TIFR, and I think, okay, all right, yeah.
all of us in that category.
All right, I'll do that.
Possible, especially since there are all these IITians here.
Yes, all right. Let me just hide this. No, I'm just trying to hide the floating controls, which I'm not getting.
You can probably just slide it.
I'll slide it down. Yeah, it'll probably go away by itself.
Escape high floating using controls for me.
Hopefully it'll go away by itself. Yeah, all right. As I said, probably the most relevant things are that I am a TIFR and I am a radio astronomer. Since we have a lot of people from IIT Bombay also here, and I wanted particularly to mention that my background is actually engineering. I did electrical engineering many years ago at IIT Kanpur, and then gradually drifted towards radio astronomy towards the end of my course. And that's what I've been doing now for more than 25 years. So I'll be talking about what radio astronomers do. I'll also be talking about how telescopes like this one work. And this telescope that we are seeing over here is a telescope built and operated by TIFR, and that's where I have been working for most of my professional life. It's not very far from here. It's between Pune and Nasik. And we do have an open day every Friday, not every Friday, I think one Friday of the month. And so, those of you who'd like to go visit it, please do. I think it's well worth a visit. With that, let me just start. I'll say more about the telescope as we go along. So I've called my talk Listening to the Universe. So, let me start by, playing some sounds of the universe for you. It'll be a little loud. I'll have to speak over it. So, just bear with me for the first slide. And then after that, that sound will be there. This is the sound of a pulsar. And it's radio waves which are coming from the pulsar. I believe the pulsar is in memory. I have been listening to this particular radio telescope, which is in the United Kingdom, the Government Bank of Telephone, and then being converted into sound. So pulsars are basically dense, rapidly rotating objects. And, to give you an idea of how dense and how rapid we are talking about, it's got a mass similar to that of the sun. So it's something as massive as the sun, but its size is only that of a few kilometers. I mean, it'll be, smaller than, say, the size of Bombay or of the order of the size of Bombay. You've got the mass of the sun squeezed down into something that size, and it's rotating at a speed similar to what your kitchen mixie would rotate at a few thousand rotations per minute. And they emit bursts of radio waves, which can be detected by radio telescopes like this one, or the one which I showed you before, the Giant Metrewave radio telescope of TIFRs. And you can do a lot of, interesting science with them, which I'll talk about later. But if you want to sort of understand where these things come from, they are created during the explosive death of massive stars. So, again, let me just show you in detail what happens in this picture. So this is now a radio image of the sky. I'll tell you later in the talk how these images were made. And you can see these shells of material. These are shells of very hot material, which are basically the outer surface of a star when it dies. Very massive stars, when they die, they explode and they throw out all of this material. And so that's formed this big shell around. And so the outer parts form this big shell around, but in the explosion, the central part gets compressed. And it gets compressed to densities close to the densities of the nucleus of an atom. And that's basically what the pulsar is. So you have this big shell of very hot ionized material, the outer part of the star, which is expanding rapidly outwards. And right at the center, you would have typically an object like this, which is very dense, size of 50 kilometers for the density of the nucleus, and very strong magnetic fields. Right, and because it has such strong magnetic fields, it shoots out energetic particles along the poles of the magnetic field, and the star itself is rotating. So it's like a lighthouse. Every time that magnetic pole is pointing towards you, you'll get a flash of radio waves, and that's what is being shown in this cartoon over here. This pulsar on the top is rotating, and you get this flash of radio waves every time that beam is pointing directly at you. And that's what I had played for you, in the earlier slide. I've just shown you the sound that you would get when this pulse actually hits your radio telescope. All right, but to listen to this thing, to hear this thing, or to observe this thing, you will need something that detects radio waves. And that, interestingly, is something which has a long history in India. Before I get to the history in India, I need to tell you what these radio waves are. So I told you it emits radio waves, and that's the thing that we detect. So these are what radio waves are. Radio waves are basically waves of electric and magnetic fields. So you have electric and magnetic fields, which are oscillating, form a wave, And these are in general are called electromagnetic waves. And there are all kinds of things which are electromagnetic waves. X-rays are electromagnetic waves. UV light is electromagnetic waves. The light that we see are electromagnetic waves, and radio waves are also electromagnetic waves, right? And what at this end is the things which are very, very short wavelengths, that the oscillations wavelength, that is the distance between the two peaks of the wave is very, very short. And those waves are the ones which have the most energy. They're like X-rays and things like that, which would actually penetrate through your body. And sort of you are able to make pictures of the bones and so on and so forth. At the other end of the spectrum, you have these waves which have very, very long wavelengths of the order of the size of a human being, of the order of a meter or so, or maybe the size of butterflies. All of these things are basically radio waves, going all the way to the size of buildings, few tens of to hundreds of meters, right? And these are waves which have very, very low energy. So the wavelength and the energy are inversely related. The shorter the wavelength, the higher the energy. The longer the wavelength, the higher. And so we are interested in these waves, the things which actually don't carry a whole lot of energy and have very, very long wavelengths. And these are the things that we want to detect. And as I mentioned before, interestingly, there's been a long history of this kind of work in India, starting basically with the work of J.C. Bose in Calcutta, who was a pioneer in sort of developing communication using radio waves. And he was the first person to actually show that you could transmit and receive radio waves. And he did this in a public demonstration in Calcutta in 1895. And many of you probably would have heard that Marconi was the inventor of radio waves, but that's not in fact the case. The first person who actually did it, radio communication, was not Marconi, it was J.C. Bose. And this is now, finally, after a gap of more than 100 years, is now officially recognized everywhere that the inventor of radio waves was not in fact, the inventor of communication using radio waves was not in fact Marconi, but it was in fact J.C. Bose. And, very interestingly, the detector that he built used crystals of a particular substance called galena to detect these radio waves. And again, this was a thing which was decades ahead of its time. So galena is basically a semiconductor. So it's one of the first uses of semiconductors in radio instrumentation. So you can see it's almost 30 years ago. Now, of course, radio waves have become ubiquitous. The use of radio waves for communication, for wireless communication, and almost anything that you would use for wireless communication, your mobiles, Wi-Fi, so on and so forth. All of these things basically work using radio waves. And what we want to do now is basically to try and build a detector for these radio waves, which will detect not mobile signals or the Wi-Fi, but will detect waves from outer space. So it sort of brings us to the question, what is there in outer space? What do we have in the universe which will actually emit radio waves? And I already showed you one example of things which emit radio waves. These very dense objects with very, very strong magnetic fields called pulsars, which, as they rotate, the beam hits you and you get these periodic clock-like signals from that pulsar. There are other things which you get radio waves from, and I'm showing you over here an image of a galaxy. But I'm showing you the image of the galaxy both in the normal light, that is, if your eyes were sensitive enough and you looked up at the sky and you could see the light from this galaxy, which is typically emitted by stars. If your eyes are not powerful enough, you would use an optical telescope. And so this image is actually made with an optical telescope. So that actually, if you were to look at the stars in the galaxy, this white stuff in the middle is what you would see. That's where the stars in the galaxy are. The blue stuff is an image made with a radio telescope. And you can see that the radio telescope is detecting material far, far outside where the stars are. Right, and what is happening is that this galaxy is actually a very complex thing. It has stars, yes, but it also has all kinds of other things in it. In particular, it has gas in it. And hydrogen is the most abundant element in the universe, and this gas is basically hydrogen. So you have this huge cloud of hydrogen, which is surrounding the stars in the galaxy. So if you were to look at this object only in optical, only using an optical telescope, using the kind of things that you're familiar with, you'd end up with a very skewed, very biased idea of what this galaxy is like. You think that the galaxy is just a small thing in the center. It's only when you look at it at with a radio telescope that you realize, no, it's actually much, much, much bigger. All right. The third thing which I have over here again, is a superposition of optical and radio images. And in the optical is, again, this colored image that you see in the background. Excuse me, I think the battery is gone. Gone? Yeah.
Jayaram, I think you have a question.
Yeah, I can take that in the meantime. Yeah.
How fast exactly do these radio waves travel?
They all travel at the speed of light, all the electromagnetic waves, regardless of whether you're talking about X-rays or radio waves or whichever they are, they're all at the speed of light. Thank you. Yeah, that's a good question. Anything more? All right. All right, so here at the back again, now it's this, an optical image with all these star-like objects that you see in it. And right at the center, you see a kind of reddish star-like object. And if that's all the information you would have, you'd say that, okay, here's an image of stars in the, in the universe, and some of them are reddish, some of them are bluish, and so on. But if you superpose this on a radio image, and this is what you're seeing in the radio image, the stuff that I've shown you in red, and you can see it's symmetrically placed around the central red object. So what is actually happening over here is right at the center, this is a galaxy, it turns out. It's a very distant galaxy. It's not a star, but it's so far away, it looks like a small point. And right in the center of that galaxy, you have a supermassive black hole. You have a black hole with a mass of maybe 10 to the 9 times, a billion times the mass of the sun. And as material flows into that black hole, it swirls around and it heats up, and the black hole again has very strong magnetic fields associated with it, pointing in this direction. And some of that material which is swirling in actually gets funneled along the magnetic fields and gets thrown out to huge distances from the galaxy. Right? You can see that the galaxy is just this dot over here, and this thing actually has been thrown out at distances which are many, 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 many times the size of the galaxy. Right? So there's something, it extracts some of the energy from the swelling in of the material into the black hole and expels material to vast distances into intergalactic space. These things are called active galactic nuclei, right? So these are other sort of phenomena that you can study using radio telescopes. And of course, all of this will have a profound influence on the surroundings of the galaxy. Right? The mere fact that you're going to throw out such energetic material into the surroundings of the galaxy is going to stir things up. It's going to sort of change all the things which are going to happen in the surroundings of the galaxy. And so if you really want to understand how galaxies form and evolve, it's very important to understand phenomena such as these active galactic nuclei. All right, so these are the things which emit radio waves. There are more, but I've just shown you a few of them, and you want to observe them. And ideally, you'd like to observe them on the surface of the Earth, because otherwise you would have to launch a satellite to see them, and that becomes very expensive. Unfortunately, it turns out you can actually detect these radio waves on the surface of the Earth. What I'm showing you over here is kind of the transparency of the Earth's outer coverings, the atmosphere and the ionosphere. When it says 100%, it means it's completely opaque. Nothing from outer space can reach down to the surface of the Earth. It's only in these places where you can see what's called the opacity falls to small values, that things from outer space, electromagnetic waves from outer space, can reach the surface of the Earth. So one small window where these electromagnetic waves can reach is the visible light. And that's very important because, that's what sustains life on Earth. All of the energy, invisible light from the sun is the thing which is coming down, allowing plants to grow, allowing life as you know it to happen, and so on and so forth. So of course, it's critically important that that the atmosphere is opaque, is transparent over there. It's actually equally important that it is opaque at these short wavelengths where very energetic rays come down, because these things actually are very harmful to life. So if the atmosphere and ionosphere were not opaque to it, it would be very difficult to form the life that as we know it now, because there would be all of this harmful radiation also falling on the surface of the Earth. So it's really, a kind of very finely tuned thing that we have life on Earth, because we've blocked out all the harmful rays, we've allowed the useful ones to come in, and allow plants to grow and allow life to happen. Another place where the atmosphere and ionosphere is transparent is this bit over here, which is exactly the radio window. So this is where we have radio waves, and all of the radio waves produced by any object in outer space could actually go all the way down through the atmosphere and ionosphere and reach the surface of the Earth. Now I really think the battery is gone. Yeah. Duplicate one. Either that or it's misbehaving. Yeah.
Is there something called as a white hole?
Oh, yeah, that's a good, that is a good question. Yeah, and it is also a little bit outside the absolute, a little bit outside the kind of things which I really know very well. I know that these things have been theorized about. None of them have ever been observed. But certainly there are people who theorize about and say such things may be there. Yeah.
Technical name is primordial black holes.
Primordial black holes. No, primordial black holes are, there are many kinds of black holes. So primordial means early. So primordial black holes are those which were formed in the very early part of the universe.
They give out more radiation. They give out more radiation than the matter we do.
The small ones do. So yeah, so if the primordials were one, I mean, that's a fun, yeah. Or I mean, okay, we can discuss that in detail, but some of them might evaporate, but those are the ones which are very small, but not all primordial black holes need to be small. And some of them actually will grow. And they are the ones which will finally grow to the size to form, for example, the supermassive black holes that we see around of a few times billion, the few billion times the mass of the sun. Sorry, you had a question.
What is the transparency between Earth's surface and ionosphere?
We are sitting at the surface of the Earth, and above us we have this column of air.
Yes.
And above the column of air, we have, ionized material, because the radiation from the sun hits the outer surface of the atmosphere and ionizes it. So we have protons and electrons and ionized material over there, right? So all of this could absorb light or radio waves of different kind. So, so that's what I'm talking about when I'm talking about the opacity, that basically if I had an X-ray which came from outer space, it gets absorbed long before it reaches the surface of the Earth. Yeah. Does that answer your question? Yeah. One minute.
Long wavelength radio waves blocked by the others seem to be blocked by the ionosphere.
Yeah. Thank you. This is done. The long wavelength, these are actually blocked by the ionized material in the outer parts of the atmosphere, the ionosphere. So the ionosphere is got these protons and electrons, and those are sort of they will because they are ionized, they actually are able to absorb waves at a certain frequency, right? And the frequency at which they will absorb will depend in detail on the density of the ionosphere. Whether it's dense or not will determine where below which frequency you would not be able to detect these waves. So I don't know if maybe some of the older people might connect to this. There used to be this thing called shortwave radio. You could listen to BBC in London and so on and so forth. Now, London is not line of sight to us, right? A radio wave sent from London would all light, including radio waves, travel in straight lines. So the only reason you're able to receive a radio wave transmitted from London is because it went up into the ionosphere, which acted like a mirror and bounced it back, and it came back to us. And so the same thing happens to a radio wave from outer space. It's like a mirror, it hits it and goes back out at long enough wavelengths. There was one more. Yeah.
So how do you find out what part of the Earth's surface exactly?
Yeah.
What's the heuristic or what's the...
No, it's these are measurements. These are measurements.
Just measure.
These are just measurements. Yeah.
So you take it all over the planet?
No, this is an average. It's not meant to be. I mean, you would have measured it in a few places, not all over the planet. You measured it in a few places and sort of averaged over it. Yeah.
Here is one.
Yeah. Sorry.
Are there any observation or observations which observe like frequencies in the roughly on the chart there is like a big gap in the 10 micrometer.
This one. Yes. So these are basically infrared light, and there are indeed observatories which work at this wavelength range, and indeed TIFR also runs some of them. It's one of the things which probably is not that well known. TIFR builds these balloons, and it's something that we've done for years, for decades, in fact. And we're probably one of the leading places in the world for balloon technology. So we build balloons which go up to 30, 40 kilometers in height above the Earth. You can see that you need to get fairly high up before you can see those rays. So we put a telescope, hang it onto this balloon, send it up and observe things. There are other people who also launch satellites and so on and so forth to observe the same thing. But on the surface of the Earth, 10 micrometers is a little difficult. All right. So if you had a telescope on the surface of the Earth, you could actually measure these radio waves from outer space. And that's exactly what started happening once radio technology became mature. So the first detection of radio waves from outer space happened in 1930s, completely by accident. And it was done by an engineer working at Bell Telephone Laboratories in the USA. So Bell Telephone Laboratories wanted to make a transatlantic link. They wanted to send radio waves, from Europe and receive it in the US and use that to communicate between the US and Europe in the 1930s. And so when you do that, of course, there'll be a lot of noise in your signal and you'd like to make the best possible, you'd like to make the noise as little as possible so you can receive whatever the Europeans are sending clearly. And so they sent Carl out to the field to measure noise, to sort of measure what all kinds of radio noise are there and what are the ways in which you could try and reduce this radio noise. And he found something very interesting. He found a source of noise which actually correlated. Some of you may know this, that the Earth, we say one day is actually 24 hours, but that actually is the time between the sun comes vertically overhead today to the sun coming vertically overhead tomorrow, right? It's the time between the sun being overhead twice in succession. If you looked at very distant stars, actually, they come overhead at a slightly different time. It's 23 hours and 56 minutes. And this has to do with the fact that the Earth is rotating around the sun, right? So you can therefore make out whether things are, near like the sun or they're some very distant object. And he found that this source of radio waves was actually repeating every 23 hours and 56 minutes. And therefore, it actually had to be some very, very distant source, and it had to be at cosmic distances. It turned out actually that he was detecting the center of the galaxy, the center of the Milky Way, right? And so that was the first sort of demonstration that there are things out there in the universe which emit radio waves. It was a very, it made a big splash when it was discovered. It was on the front page of the New York Times and all that, but none of the astronomers bothered because the astronomers at that time all did optical astronomy. None of them understood radio waves or radio technology. And, so nobody followed it up and that was that, right? He discovered radio waves from the center of the galaxy and it was a kind of, it was a curiosity and that was it. The only person to follow it up was an amateur called Groth Reber, who built a small telescope in his backyard, and he continued to work through, detecting radio waves and so on. And but really nobody was paying any attention to radio astronomy for a long time. What changed was World War II. In World War II, there was a very rapid development of radio communication because you needed it for radar, you needed it for all kinds of things. And so there were all these kinds of pieces of equipment which were built for the war. This is actually a radar system. It's actually a German radar system, which were, and many hundreds of these were built during the war. And after the war, all of these pieces of equipment were surplus. And therefore, the same people who had built them, which often turned out to be, the electrical engineers from universities around the world, these people began to think of what else can I do with this piece of equipment, which is surplus. And one of the things they decided they got curious about is now, can we use this to detect radio waves from outer space? And so, immediately after the war, there was this huge explosion in radio astronomy, and radio astronomy really began to grow. In India also, the work in radio astronomy started pretty much at the same time. This is the first radio telescope built in the country by the Indian Institute of Astrophysics in 1950. So you can see that things actually began pretty much at the same time in India as it did elsewhere in the world. At TIFR, got into the game a little bit later in the 1960s. So in the early 60s, a group of radio astronomers who were working abroad had written to a number of Indian institutions saying that they'd like to come back to India and they'd like to start up this new field of radio astronomy in India. They wrote to many, many people, but the only person who actually responded was Dr. Homi Bhabha, who agreed that he would set up a radio astronomy group at TIFR. And this is the telegram that he sent to one of the people in the group, which basically says, stop reference proposal from Menon, Kundu, Krishnan, and yourself, forward by Menon in September. We have decided to establish a radio astronomy group. Stop, letter follows, stop. Right, so this is basically telegraph technology, which probably the younger people have never seen, where you put a stop to indicate that the sentence has finished. Right, so, and again, since I'm putting up this telegram, I should mention to you that one of the good things I think that TIFR has done over the decades is to maintain our archives very well. We really have an absolutely wonderful archive of, of what all happened at TIFR in the early years. And it's a great reference for science in post-independence India. Among other things, I've shown you this letter which went out to Govind Swarup, who would be, one would regard as the father of radio astronomy in India. Some of you may not also know that Abdul Kalam also joined the space program, a little bit later than this. But at that time, TIFR and the Department of Atomic Energy were very deeply involved in all of this. And so Abdul Kalam's interview was actually held at TIFR, and the offer letter also went out from TIFR, and that is another bit of history that we have in our archive. So those of you who are interested, at some point when we have open days, do look at our archive. We really have a fascinating history of the birth of both the atomic energy as well as the space program in India. Anyway, so Dr. Homi Bhabha sort of offered to set up this group. And TIFR began radio astronomy in 1963 when Professor Govind Swarup moved from Stanford to TIFR. And he started work pretty quickly. He built the first radio telescope of any major size in the country. And this was built not very far from here in Kalyan. Right? So this is, at that time, this is what Kalyan looked like. And there was space available. So they set up this whole array of telescopes, and they used it to observe the sun. But very quickly, they moved on to a much bigger telescope, which they set up in Ooty. So this is the Ooty radio telescope. I don't have anything in the image to give you a feeling for the size, but maybe just seeing the trees over there in the background would give you some idea. This telescope is more than half a kilometer long, right? So it's this enormous mechanical structure. It's half a kilometer long. It's built on a 10-degree slope for reasons which I can explain to you later. And it was a massive engineering challenge, you can imagine, both mechanical as well as, much of the electrical and electronics components were not available in India at that time. And a lot of indigenization happened, which again was very important to sort of seed the growth of all of this technology in India. Right. So this is Ooty radio telescope was used for a number of things, for studying, cosmology, for studies of the gas between stars, for studies of pulsars, which I showed you one before, studies of the sun and the material around the sun, and so on. It was built, it was started operation, I think, around 1970, and it's still working strong. Yeah? So it's, even though this telescope is now more than 50 years ago, it's still, doing well and delivering science.
This is a half a kilometer thing that can move?
It can move. Thank you for asking that question. So it's not just half a kilometer long. It actually rotates along this axis that you can see over here. This is a kind of pipe, which is the axis of this telescope, and you can rotate it from east to west to follow whatever object you're looking at as it rises and sets. So yeah, so it was quite an engineering marvel at the time it was built. Okay, so this is the other big telescope that TIFR runs. It's run by the National Center for Radio Astrophysics. Professor Govind Swarup, whose photo I showed you over here, started out in Bombay and then very quickly moved to Ooty. But as the group grew bigger and bigger and its activities grew larger and larger, they finally sort of established an independent center, which is now called the National Center for Radio Astrophysics. It's in Pune, and it is the one which operates now both the Ooty radio telescope as well as this telescope, whose picture one I'd shown you before, which is a giant meter-wave radio telescope. So this is basically what you would imagine a telescope looks like. It's a mirror. You'll ask me, where is the mirror? You can't see the mirror because what we are looking at is radio waves whose wavelength is very long. I told you that its wavelength would be of the order of the size of a human being. So if this mirror has holes in it, which are small compared to my height, it just doesn't matter because, as far as the radio wave is concerned, it's a perfect mirror. So there's a mesh, there's a fine wire mesh on the surface. You can't see it. But the radio wave sees it definitely. For the radio wave, it's like a solid surface. It just comes, hits it, and sort of gets reflected back. And gets reflected back into the small antenna over here, which is what we call a feed antenna. And over there, it's converted into a tiny little electrical voltage. And then you have very sophisticated electronics, which amplifies that voltage. It's brought down along cables along one of these arms. It goes to the center of the telescope, gets amplified again, gets converted into an optical signal and sent off along an optical fiber many tens of kilometers down to where it is received. Right? So it's basically, you could regard it as a kind of photon buckets. It's collecting radio photons. All the radio photons which fall onto this is collected over here, converted into an electrical signal and sent off. Right? And this telescope also sort of, you can see its mechanical arrangement. There's a gear over here which allows it to rotate the way my head is sort of turning, up and down. And it also has this other sort of yoke mechanism which is attached to a gear over here, which allows it to turn round and round. So it can sort of move on two axes and can therefore point anywhere in the sky, wherever you want it to point. Right. So, and I need to tell you something more about waves before I can explain to you why the GMRT has been built the way it is. And what I need to tell you is that waves actually undergo a phenomena called diffraction. Light, you've been taught, travels in straight lines. More or less true, but not, it's not the whole truth. They can actually sometimes bend and spread out. So, and that's a general phenomena for all kinds of waves. So here I'm showing you water waves, waves in the ocean. You can see in the distance, they're basically, the wavefront is basically this line over here. So you have waves coming in like this parallel to the shore. And they have built over here a wave breaker so that, the waves don't actually reach the shore and start sort of, eroding the beach over here. So they built this barrier to prevent the waves from actually coming and hitting the beach. But this barrier, as you can see, has got damaged. And there is a small part in the middle where the barrier has broken. And you can see that the waves, once they've gone through there, are no longer coming in straight lines. They're now spreading out. They're spreading out in all directions, right? And they've sort of formed this semicircular thing. And that's because of this phenomena called diffraction. And that's the same reason why if you make images with a telescope, they won't, even if you have a star which is like a point of light, when you make the image with the telescope, because the telescope has a finite size, which, sort of the waves get spread out a little bit, and the images that you see will get blurred a little bit. So that's what you're seeing over here. This is the Hubble Space Telescope, and you can see that the stars are not point-like. They actually have this fuzz around them, and that's because of this phenomena of diffraction, because the light spreads out a little bit. And the amount it spreads out depends on the wavelength of the light and the diameter of your telescope in this ratio. So that means if you're working at very long wavelengths, if you don't want it to smear out very much, you need to build a very, very big telescope. And how big? So for example, here, if I look at optical light, you can see its wavelength is of the size of, somewhere between protozoans and molecules. And, if I wanted to have the same kind of resolution over here, I need to go, I need to build a telescope whose, which is as much larger than the optical telescope as human beings are to bacteria, to protozoans, right? So I need to build this very, very big radio telescope if I want to have the same resolution in my radio telescope as I get in an optical telescope, right? And an optical telescope, it turns out that the resolution is not really set by this limit of diffraction. It's actually set by turbulence in the atmosphere. So turbulence in the atmosphere anyway disturbs the light as it comes out. It spreads it out a little bit, and it limits it to to things of the order of 1 arcsecond, right? And so if I wanted to work with a radio telescope and I wanted it to have a resolution of the order of 1 arcsecond, it would turn out that I would need, simply because the radio wave is so much bigger than the optical wave, I would need a radio telescope which is about 200 kilometers in size, right? So it's just a huge difference. And so, for example, this tiny optical telescope over here, which has a diameter of only this, would actually have an angular resolution which is much better than this, which is one of the largest fully steerable telescopes in the world, which is 110 meters across. Even though this is 110 meters and this is maybe only about half a meter or so, this thing actually would make much sharper images of optical light than this would of radio light. And to just give you a rough feel for what what the difference would be like, I'm showing you now 2 pictures of the moon. This is a picture which you've taken with an optical telescope, and it would have typically, sharpness of the order of 1/2. And I just blurred it out. I haven't blurred it out to, something as bad as what this telescope would see. It's probably only about 1/3 or 1/2 as bad as that telescope would see. But nonetheless, you can see that we've completely lost all the features. All you see is that, there's this kind of, roughly spherical blob over there, and that's what the moon would look like if you were looking at it with a radio telescope. Particularly, for example, with this radio telescope, it'll actually look a lot more blurred than that. But that's not what you would like, right? You would actually like to be able to see this thing with the same sharpness, with the same clarity as you do in your optical telescope. But as I told you, that actually sounds like a terrible problem, because you need to build a 200-kilometer size telescope. Give me a moment.
Wow.
Yeah.
Because it is blurred with the bigger one. So you've got a bigger diameter.
You've got a bigger diameter, but you're also working at this much longer wavelength. Your wavelength is of the order of a human, whereas instead of working over here in the visible light. Because you've switched, instead of working in the visible, you're working in the radio, you need to build, a telescope which is that much bigger.
No, I get it. So you've got a longer wavelength. Won't the image be much clearer because your more radio waves will be reflected?
No. The longer wavelength, okay. I can work through, I'll take that question offline. I'll just, go back to this, and as to why this happens, we can talk offline. But basically, this is the ratio which matters as far as sharpness is concerned. The ratio of the wavelength to the diameter.
Oh.
So the longer the wavelength, the bigger the diameter you need to get the same sharpness.
Oh.
Why this is so, we can talk about later, but yeah. What happened?
What connection issue? Yeah, okay, it's back.
Go back. All right, so this is what it would look like. And, to just give you an idea of what a 200-kilometer sized object would look like, I superimposed it on a map of Maharashtra, right? So if I wanted to see the moon with the same kind of sharpness that I would with, the optical, that small half-meter size optical telescope, I need to build a radio telescope which was this size, which is obviously an impossible thing to do, right? So radio astronomers go about getting sharp images in a completely different way, and they use a different, property of waves. And that property that they use of waves is that waves actually interact with each other, and they interfere with each other. And I'm showing you a picture of here again of water waves. And there are two sources of water waves. You've got something making water waves over here and something making water waves over here. And they're both sort of spreading out. But you can see that, the waves from here are interfering with the waves from there. And, there are regions where it's much brighter. There are regions where it's much darker, right? So these two waves are basically the waves which are coming from here and the waves which are coming from there are interfering with one another in some way. And basically what is happening is the following, that, in regions where from the first source, the wave was sort of exactly, misaligned with the other one. That is, every time this one reaches the bottom, this one reaches the top. When you add them both up together, they exactly cancel out. On the other hand, when you have waves which are exactly aligned, that is, they both reach, peak at the same time, they both sort of have their minimum value at the same time, they add up and you get a much bigger wave, right? So that's really what's happening over there. That's what's producing the pattern of brightness and darkness, right? And, I showed you a very simple thing where I just had two sources over here. In the sky, we have many, many, many sources. And it turns out the interference pattern that all of these sources produce will depend on the structure on the sky. So if I can measure that interference pattern, it turns out if I can just measure this pattern, I can invert it and tell you what the sky looks like. And that exactly is what radio astronomers do. They sit on the surface of the Earth, they measure the way in which the radio waves from different sources interfere with each other. And having measured that, they're actually able to make an image of the sky. Right? And so that's how most modern telescopes would work. You don't have one radio telescope. You have radio telescopes spread along, along lines. And these, because they are spread out, can actually measure that interference pattern of the different radio waves which are falling out on the surface. Having measured the interference pattern, you do some computer magic, and you invert it, and you get back to the image of the sky. The bigger your array is, it turns out the sharper your image would be, pretty much as you would have expected, because I told you it depends on the ratio of the wavelength to the diameter. And if I make an array which is very, very large, it's like I made a telescope of very large diameter. So I don't have to cover 200 kilometers of Maharashtra with a reflecting surface. I can just dot it with a few telescopes. I can put a few telescopes here and there, and then I can combine all of their signals with in my computer. And that's good enough for me to be able to make an image of the sky. And that indeed is what the giant meter wave radio telescope is like. It's an interferometric array. I'm sorry, the image is a little bit washed out, so you can't see it very clearly. But there are actually 30 antennas which are sort of spread out. It's not quite 200 kilometers, but it's spread over an area of about 30 kilometers. It's used a very, very novel, cost-effective antenna design, which was conceived by Professor Govind Swarup, who I had spoken about earlier, spread over an area of 25 to 30 kilometers, connected to the central electronics building by optical fiber, and completely built and designed and built by NCRA-TIFR, and it was dedicated to the nation. This is sort of just showing you the antenna layout of all of the 30 antennas, and it was dedicated to the nation more than 20 years ago by Sri Ratan Tata, who is the chairman of our council. All right, so that, of course, we haven't kept still since then. In 20 years, technology moves a long way. And just a few years ago, we completely upgraded the telescope. And basically, the main thing that we did, it involved a lot of work, but the thing which really mattered was that we changed something called the bandwidth from 32 megahertz to 400 megahertz by about a factor of 10. And that actually made the telescope significantly more sensitive than it was before. Earlier, I told you that telescopes are like photon buckets, right? They're collecting all of the energy which comes in. So, here you have a bucket that's collected all of the energy which fell in. Here's a bucket which is of the same size. But you're actually doing your measurement over here. That is because we have a pipe, right? That optical fiber or whatever it is that we had, which took the signal from the antenna and brought it to your building. So earlier, you could imagine that the same analogy, we had a very small pipe. We had a narrow pipe. It didn't bring us much of the signal. Now we have a much broader pipe. It brings us much more of the photo energy in the photons which was collected. It brings it down to our central building. And because now we have this much bigger pipe, we get much more, many more photons at the end of the pipe, and we can do much more sensitive observations with the telescope. Just continuing on the giant meter wave radio telescope and connecting it to some things I told you before. In 2021, not very long ago, it was declared an IEEE milestone, which basically is IEEE is the International Institute of Electronics and Electrical Engineers. It's one of the largest professional bodies in the world, and it recognizes major milestones, major scientific and technological achievements by something that it calls a milestone. So the GMRT was declared a milestone in March 2021, and that puts it in very, very distinguished company because there are only 3 in India of these milestones. The first milestone was of J.C. Bose, which I mentioned a while ago in 1895. The other one was Raman's Nobel Prize winning work, and the third is the giant meter wave radio telescope. All right, yeah, thank you. Go on. No, it's 11:45.
No, it's okay. I think
All right. I'll tell you just a little bit about the science with the telescope. I have a lot of science that we do with this telescope, but we can pick up during question answer session. So I'll tell you, because I started with pulsars, I'll start with pulsars over here. I told you that pulsars are things which rotate, and they rotate in a very, very predictable manner. And so they're like a clock. They're like a naturally occurring clock. That pulse from the pulsar comes to you at a very, very predictable time. So because they are such predictable clocks, they become very, very, good probes of all kinds of things. So for example, some of you may have heard of gravitational waves. For example, when you have supermassive black holes which merge, they sort of produce gravitational waves, which will then sort of propagate through space and sort of disturb the fabric of space-time. So if you want to measure that, there are many ways of doing it. But one of the ways, particularly if you're talking about supermassive black holes, is to use these pulsars. So basically, because you have this clock, this very accurate clock sitting between you and the wave. So as the wave goes by, effectively what it does, you can imagine it as stretching and sort of narrowing the space between you and the pulsar, right? And so that means, therefore, that when it stretches the space, the pulse from the pulsar will take a little longer to reach you. When it narrows that space, the pulse reaches you a little faster. So that pulsar's pulse will no longer be that, it will no longer come at the time that you predict. It'll come at a slightly different time. Oscillation, because the space itself is sort of, it's dimension setting. And you might remember, so about, I think in June or July of last year, there was a very major announcement of the detection for the very first time of gravitational waves from supermassive black holes. And this was done by a whole array of telescopes spread around the Earth. There were 3 teams, basically, which announced it more or less at the same time. And one of the teams which announced it at the same time was an Indo-European team, which used a fair amount of data from the upgraded GMRT, right? And that data actually turned out to be very important to sort of correct for various sort of biases and problems that you might have while trying to do this exercise. And that's the thing which allows you with great precision to tell you when the pulse should have come and when it actually did. And therefore allows you to infer that there were indeed these merging supermassive black holes out there which are sending gravitational waves, which are disturbing the space between you and these pulsars, and therefore sort of changing the times at which you would receive the pulsar. Yeah.
What is the space between the pulsar and the radio telescope where narrow and contract and stuff?
Yeah, it is basically, that's what gravitational waves are. They're disturbances of the space-time fabric itself. So, I mean, it's connected to Einstein's general theory of relativity, which basically connects gravity to curvature of space-time. So, so gravitational waves will actually change not the pulses. It actually changes for the distance you could imagine between you and the pulsar when the wave goes between you and the pulsar. You could imagine it as a wave in space. It's a wave of space. Space itself, I mean, very, very naively speaking, is expanding and contracting.
And these black holes, when they combine, that's when the gravitation force gets formed. So do these things events occur very often with the combining of 2 black holes?
They do. So you can. There are many thousands of these objects in the universe. So basically, almost every galaxy will have a supermassive black hole in its center, and many galaxies will merge over the age of the universe. And when the galaxies merge, very often the black holes at their centers will also eventually merge and form a still bigger black hole. And in the final stages of the merger, when they're doing that final sort of spiraling around each other before they actually merge, is when they produce these very strong gravitational waves.
So how often would they
I'll have to get back to you on that. There are many thousands, but how often they occur, I'll have to, it depends on the volume of space you're looking at. The bigger volume of space, the more of these objects, the more often you would have. Yeah.
The Milky Way galaxy.
The Milky Way galaxy has only one supermassive black hole in its center, so there's nothing to merge with it. Yeah.
Is the question?
Yes. Yes. Yeah, that's a good question, and that's because we are talking about waves of different frequency. So these are waves which have, periodicities of years. The gravitational wave detector has arm length, the effective arm length over here is monstrous between you and the pulsar. The arm length of the laser interferometers are a few kilometers. They detect much narrower, much shorter wavelengths, things which are much higher frequency. So they detect stellar mass black holes, not supermassive black holes. So they detect completely different kinds of objects. Yeah.
I think we should go on.
Okay.
So I will get you.
All right. I'll do one more and stop. I just want to talk about this, which all telescopes are time machines, not just radio telescopes. And that's something all of you know, that the sun, the light from the sun takes 8 minutes to reach us. That means we don't see the sun as it is now, we see it as it was 8 minutes ago, right? We're looking into the past of the sun. One of the nearest stars to us is Alpha Centauri. It's at a distance of 4.3 light years, which means we don't see it as it is now. We see it as it was 4.3 years ago. And the galaxies that the telescopes can detect these days are very, very far away. The light from these galaxies actually takes a billion years or more, or giga-year, a billion years to go from the galaxy to reach us today. So that means we see this galaxy as it was a billion years ago. Right, and so therefore we can actually study the evolution of galaxies. We can see the galaxies near us today. We can understand the population of galaxies near us today. And using telescopes to observe galaxies which are very, very far away, we can see the population of galaxies billions of years ago. Right, and so this allows you, even though you're sitting on the surface of the Earth and you're observing now, you're not observing in the past, you're observing right now. Just by looking at galaxies that are further and further away from you, you can see things as they were in the further and further past, right? So you can actually study the evolution of galaxies. You can study how galaxies started and how they ended up looking like the galaxies that you see today. And one of the things which has been known for a long, long time is that galaxies, there are stars in galaxies, of course. These stars were not there when the universe was formed. They formed at some point. Right, and you can ask the question, when did these stars in the galaxy form? Or the other is, what is the rate at which stars form in galaxies? And that's what's being shown to you over here. This is the rate at which stars are being formed in the very early universe, more than 12 billion years ago. This is the rate at which stars are being formed today, right? So this is the time in the past. This is 12 billion years ago, this is today. And if you look at it in the distant past, galaxies were not forming stars very fast, right? There was a very low rate at which they formed stars. Then it, grew very sharply. And there was a time about 10 billion years ago when they formed stars at a very, very rapid rate. And then again, it started declining. And today, again, they form stars at a much, much lower rate than they did about 10 billion years ago. So this is something which has been known for a long time. From our observations with optical telescopes, we can measure the rate at which these stars form, and that this is the way in which the star formation galaxies in the universe evolved. You can ask the question, why? Why did this happen, right? So one obvious answer you could think of is that maybe something is happening to the gas, because the stars form out of gas. The gas collapses and forms stars, right? So, one of the simplest picture you could say is that maybe what is happening over here is at least, in this part over here, for example, you could conjecture that, after having gone through this massive burst over here, the galaxies somehow are running out of gas, that they don't have a whole lot of gas, and they don't have a whole lot of gas, they've used up their gas, there's nothing much left for them to form. You don't have the raw material, and therefore, the star formation is gradually dying out. And you could conjecture that, but if you actually want to check it, you'd actually have to measure how much gas is there in galaxies in this different periods of the past. And that is something which is very difficult to do because it requires very sensitive telescopes, and it's only very recently become feasible. As I mentioned to you, the GMRT went through an upgrade, which made it much, much more sensitive than it was in the past. And that allowed us for the first time to actually start measuring how much gas there is in galaxies over here. How does it compare to gas in galaxies over, in the current epoch? What was it like 8 to 10 billion years ago? What is it like today? And compare the two. And it appears indeed to be the case that these galaxies over here have a whole lot of gas, and that they're actually running out of gas by the time that they form over here. Sorry. Yeah. Right. And so we are actually able to measure it. And, this very interesting observation made by Aditya Chaudhary, Nitin Kanekar, and others at the National Center for Radioastrophysics, that the galaxies actually were much more gas-rich in the past, and then they are running out of gas, and they're somehow unable to accrete enough gas from the intergalactic medium around them to actually sustain their star formation. So the reason why the star formation over this period is actually declining is simply because there isn't enough gas left in the galaxies to form stars. All right, I'll stop over there. I have many, many more things that we can talk about, but we could perhaps do it in the question and answer session. Thank you.
Okay, so it's coming up to 12 o'clock. So I think there's a lot more to go. I know you've asked some questions in the middle. Online audience, if you have any questions, this is the time for you to put it down in the chat. We'll try and take them. Meanwhile, just before we break, I should also tell you that 2 weeks from now, we are going to be having Badal from the Department of Biological Sciences at TIFR, who will be telling us about stuff happening inside cells, in short. And then a month from now, 7th April, the next session here is going to be
about live
Rajarshi, who's just finished her PhD or close to finishing her PhD, and their lab has got some really new results where inside a live cell, they can actually look at molecules of fat, lipids, and they can sense these, and sensing these is very critical to determining some disease conditions, etc. So it's a very new work that has been done in the chemistry group. That's going to happen 7th April over here. Before that, this month, March, happens to have a 5th Sunday, 31st of March, the last day of March. And we will be live from a lab in TIFR. That's, of course, online only. That's like a virtual lab tour. We'll let you know about that. Just follow us, or I'll let you know how to do that. So any online questions?
Yeah.
Yeah.
Are electromagnetic waves necessary to detect gravitational waves? That's the question.
To detect, I mean, all the detectors of gravitational waves use electromagnetic waves that I am aware of, because interference is actually a very good way of measuring distance, changes in distance. And so interference of electromagnetic waves is how these very sensitive detectors are built. Yeah. Although gravitational waves are not electromagnetic waves.
I guess.
Can I add to that? So speaking as somebody who teaches the experimental methods class, in today's world, the only thing you measure is either a voltage or a current. So whatever you're trying to measure, whether it's a gravitational wave or a radio wave or an optical wave, finally you need a detector that measures something, which eventually brings you back to electromagnetic waves.
I think there is no other question right now.
Okay, so on that note, we'll stop the live stream. Sorry guys, no chai for you. Everyone else, let's just go out, have a quick cup of chai and come back in again. I'm sure there's lots of fun.